title that was in the indico. So I will talk about impact and mitigation of uncertainties in particle therapy treatment planning now. Since I think also in the previous talk, we already heard about like the basic uncertainties, and I don't want to now start talking about the sides of motion and so on, and what are the sources basically again, but I want to show you um, like, let's say, dosimetric impacts actually, and what planning techniques we have to work those out. Um, okay, maybe let me continue here and switch to the laser pointer. Okay, so if you also remember my presentation from yesterday, there was at the end like a short excursion towards uncertainties, and I already showed these images. So, and we had it in the last talk especially. So there are um, multiple sources of uncertainty in treatments in general. It's not limited to particle therapy. So also to photon therapy. There's like, just as you see here, problems with patient setup. So the patients are not always in the exact same position. So there will always be some uncertainty, some daily variation during the fractions in that. Joao Seco also showed like the motion that can happen within the patient, breathing motion, other motion of the intestines, like any anatomical change can affect your treatment within the fraction while you are irradiating, and of course between the fractions. So like patients are basically getting instructions on what to do before treatment. So please go to the bathroom and stuff like this, or like with time schedules, please don't eat, and so on and so on. But still, you cannot, like, it's probably, I would say, it's a basic rule of science. You cannot reduce uncertainty to zero as soon as you go to a practical environment. Um, so there will always be some kind of uncertainty you need to mitigate. And we have seen a lot of techniques that we try this, particularly in particle therapy, with imaging that we do during the treatment and so on, and taking better images upfront. So, and we will now maybe first quickly make a very short summary. So we have like this daily patient setup, the interfractional motion, preparational uncertainties. We already had this planning CT, dual energy CT. Of course, also machine setup. Your machine might not produce exactly what you wanted to produce. There might be slight differences and so on. And the classical way to deal with this during planning, let's say that's what we do in photons, like almost all the time, is, and I also showed this yesterday, these addition of margins. So in addition to the volume that you see during treatment, like this, or during imaging, during initial imaging, this gross tumor volume, which you define based on multiple images. Like I think it was also said in the last talk again, you have the CT that you also use for planning. You take MR images maybe for, or PET images. This information then goes into the definition of this GTV on the planning CT, and to some extent also in the definition of the CTV. But this is mostly kind of an delineation based on experience that expands the GTV in a certain sense to include regions where you don't see tumor, but from experience and medical knowledge, you know there should be tumor. And the uncertainties that we saw before, like all these motions or other things, you usually encode into a planning target volume where you say, okay, that's my safety margin. I know within this margin something might be happening. So my patient might slightly shift or so, and so on. These margins, if you have a very static anatomy, they can be really kind of very simple. You say, you make some, you have a margin recipe, I come to that, and you say plus, and it results in plus minus 5 millimeters, and then you make an isotropic expansion of your CTV, and then you have your PTV. If you have movements, you basically can analyze the movement pattern and then say, okay, That's how I define my PTV. There's an intermediate step of creating the ITV, how is it called, which then includes only the CTV movement, and then you put the PTV on top. But that's basically how it works. You create these margins. So, and when you can ask the question, yeah, really, does this work? I mean, you should have now seen some information and images that basically told you might be not the best idea. Taking the original, let's say, margin recipe, which is often cited and was developed by Marcel van Herk, is basically it kind of does some simplified assumptions on the uncertainties you expect. So basically it divides your uncertainty into a systematic part, so something that you expect that happened in preparation before the treatment, and a random part, something that happens on the day of the treatment. And given these two parts, you basically say you can make some estimations on how the dose degrades and so on, and then you set a threshold what you want to achieve. So you want to achieve dose coverage of 95% for 90% of all scenarios that you can imagine, and then you come up with a recipe. So the detailed process of deriving this can be like read up here if you're interested. And if you do this for, let's say, a photon treatment, and you see this is kind of a, so I can count, yeah, 5-beam photon treatment. So what you see here is this like olive green, I don't know if it's olive green, I'm bad with colors, is the CTV, and you have like a small PTV, like an isotropic expansion of the CTV that constitutes the PTV. And this PTV now captures like this setup, or like this uncertainties you assume with this recipe, and then you see that the high dose region is basically always or almost always covering the CTV. While the PTV often falls into the gradients, the CTV stays covered at almost all times. So basically, if everything would be absolutely ideal, you would always have 95% of the prescribed dose be covered in 9 out of 10 scenarios, in a sense. So that's how you could think about it. So using margins is, however, not so easy in particle therapy, and I give you a very let's say strong example on that, one that basically covers interfractional movement in the intestines, which can be quite drastic, as you see here. And basically the margin is not drawn in here, so that's like a 4D CT taken in between like days across the treatment, and you see that on the contours, that basically the contours change quite a lot in this actual slice here. You see the lungs popping up here, and then you see like some changes here, and this is like very substantial changes. And also the CTV, which is this blue thing here, changes quite a lot. And if you would like to basically plan this whole treatment with a margin, so the margin is not visible, but you see it basically, it's like really big, because we already know that proton therapy or carbon therapy requires, basically due to range uncertainty and so on, quite some big margins. So you work with a big margin, but the big margin, even if it's like huge, it's almost twice like the diameter, I guess, of the CTV. It still is not able to ensure a high dose coverage at all times. You see, there's basically sometimes even like higher dose coming in, then there is like a small cold spot here coming in. So to some extent it works, but it also hugely creates like this high dose region that also falls into the organs then. So it's two things. On the one hand, your initially homogeneous dose that pops in at like one of the images regularly gets like degraded all the time. Like in each other scenario, these range uncertainties, namely, for example, going through lung here instead of dense tissue, just basically completely degrades this IMPT plan. So maybe for completers, this is a full IMPT plan, so or everything has been optimized. So the answer to this question's margin really is, I would say, especially in moving anatomies, like first a no, especially when you use such a generic recipe. There are some attempts to do this with like adapted margins and so on. So then this becomes a little bit better. So you can adapt margins for expected range uncertainty. And if you have a very static anatomy, like that is very close, like where you have almost no heterogeneity in the anatomy, margins might also work. And so it's not a definite no, but in the usual case, like, or in general, you would say, no, it doesn't work in a lot of cases in particle therapy. Okay, this was like the aspect just based on motion, or like it's like setup of the patient during the whole course of the treatment. The other thing that was mentioned in the previous talk is, and I also mentioned it yesterday, that when we take a CT, what units we get out of it is Hounsfield units. And Hounsfield units is just basically a measure of how the photon beam is attenuated in the medium, or better say in the voxel that you measure. So it's like you have a small element and you say the photon beam is like attenuated by this amount in this voxel. And these are not the relevant quantities for ions. The relative quantity for ion is like stopping power, which is dependent also on the mean excitation value and the electron density. So that's not a quantity that you get. Looking a little bit more closely on what we require for those calculation, we have like, let's say, two main types of those calculation. Also repetition of yesterday, we have the deterministic algorithms that that basically rely on previous measurements and simulations in water. So they basically scale the dose in a sense by using water equivalent path lengths, which relies on knowing the relative stopping power. And for Monte Carlo, you would basically know more about the material that's inside the patient. So because you have different cross-section based on what material is in a voxel. So is it a lung tissue? Is it bone? Is it air in the lung? Is it a mixture? And so on. And you require, of course, like material properties like the density. And what is usually done is that you basically just take a lookup table and you have some measurements, and you have some calibration data, and with that you basically calibrate such a calibration curve that you see is not able to capture all the variation that you have in your data that you use for calibration. So you are absolutely sure that there is some error in this calibration to water equivalent path length or relative stopping power given your CT. And that's what is often referred to as range uncertainties. But I want to make sure that basically this I don't really like to give an absolute number on the uncertainty there, because it also depends on the imaging technique. You can take dual energy CT, and then you have different techniques of estimating this relative stopping power. But this, while this is often called pure range uncertainty, like setup shifts and anatomy changes are often creating the larger range uncertainty, because your Bragg peak moves, or like your pencil beam, your beamlet moves from passing like just soft tissue to passing a bone or passing air. So that's also creating a range uncertainty that is caused by a shift or something like this. So when you hear range uncertainties, always be sure about what is meant. If it's like this direct range uncertainty that comes from the calibration. And can you please mute yourself, Jacopo Valsecchi? Sorry, would be nice. Thank you. So how do we quantify the impact of those uncertainties? And there's basically multiple schools on how to quantify this. And I would say the most popular school is using the robust worst case approach. So what are we doing there if we want to basically see how this uncertainties that we saw impact dose and then use it in treatment planning later. The robust worst case approach assumes basically you have some knowledge about your input uncertainty. So you have a magnitude, for example, the CT calibration is like introducing 3% uncertainty or something like this. And the patient setup error could be 3 millimeters. Maybe you have a 4D CT and so on. And you take discrete scenario sets. You create a scenario set given like discrete realizations of these uncertainties. So for example, a 3 millimeter shift, a 3.5% overestimation of the RSP and underestimation and so on. And then you do a repeated dose and plan metric calculation and you end up with like for your dose or plan metric, for example, the mean dose in an organ, or like it can also be an objective like the squared deviation of a prescribed dose, you end up with values and you have a worst case. So you don't, it's not usually clear what exactly from these scenario set then constitutes the worst case. So depending on the plan metric, like for the one plan metric, it might be this scenario that creates the worst case. For another, it might be this. So a range overshoot might create like the worst case in an organ directly behind the brag peak, but some other metric might be even better than you don't know. So the worst case is like the scenario which is the worst for this metric given like these scenarios. And then you can use this in optimization. I will come to that. So you can use like something like minimax approaches, voxel-wise worst case approaches. I will introduce them a little. But you also have limitations. So basically when you optimize this, you enforce robustness on the worst case. So basically when you look at your worst case, you can always say, I have my worst case is now this, and I can like say my treatment is super unsafe given my worst case, or it's super safe. But especially when you use it in planning, you really have to think, is the output worst case really among my input worst case choices here? Isn't maybe a scenario in between creating a worser case? Maybe even a scenario that is more likely than my worst case chosen here. So there are some limitations there. And the complexity here depends heavily on the number of uncertain variables. So you a lot of you heard probably about the curse of dimensionality, and assume like if you have like an uncertainty in shift, an uncertainty in range, then you have a for DCT, then you have an uncertainty in some other parameter. In biology, you basically create an uncertainty space where the interplay of uncertainties can no longer be really captured unless you do like hundreds to thousands of those calculations. And just to give you a number, what is often used, like when people today plan with robustness scenarios, it's like 9 or something like this, maybe 20 something if someone is really, but usually you do overshoot, undershoot, shift, maybe combined with a 4DCT, and that's the space you cover. So it's really not a big uncertainty space you cover with this. So let's look a little bit more about the optimization techniques. So you describe your uncertainty with scenarios from a discrete uncertainty set. And during optimization, you evaluate, for example, all objective functions and act on the worst case. That's the minimax technique. So basically minimax, because your solution to your optimization problem is you search the minimum of the maximum over all scenarios. And you can also put constraints on each scenario. So given like this, how to talk about it in a prescription way that we had yesterday, you would minimize the maximum mean lung dose, for example, from all scenarios. So would evaluate all mean lung doses and then say, like, now I want to act on the worst scenario of those. And you could have constraints but this part sounds again more easy than it actually is. It is it takes a lot of computational effort, depending on the method. Like different ways to do this could also be, again, taking all these scenarios and then just make a different combination of how to describe the maximum. So you could do like a voxel-wise combination, for example. So you create an artificial dose distribution that's at minimum, that takes the minimum dose. So you basically have an artificial worst case dose distribution now, and the other way around in the organ. And then you basically have an optimization problem where you have where you optimize always the worst case dose. So it's like one dose distribution. You don't always have to evaluate all your objectives and then choose the maximum. You just evaluate all objectives based on the artificial worst case dose. So this, for example, then minimize the mean of all maximum voxel doses from all scenarios. So it's a little bit different. And I don't want to go into the detail what differences these methods do. So in general, voxel-wise, worst case um, is a little bit more conservative, but there's a lot of publications to read up on this. But that's just to show you that you can use this technique of creating these uncertainty scenarios for optimization. And just to look on our previous example on how this would look like. So we have this conventional plan that is completely degraded by these uncertainties. Please mute yourself. Pravid Waban, please mute yourself. It's kind of, could you please mute yourself? Thanks. So basically we have this conventional plan here that is completely degraded during the scenarios. I don't want to basically, I put something else here to not tell you there's not other ways to go with it. So if you want to make this margin approach work, what is often done as an intermediate, like as a compromise solution, and also often done in centers, is that you optimize each beam independently, which makes the plan more robust, but you still need the very large margin and still have a lot of it still doesn't mitigate the problem of your organs or something like this slipping into the margin. But when you really use these scenarios, these uncertain scenarios that here are explicitly computed as image variations, let's say, you basically allow the optimizer to create a plan that is really tailored to these uncertainties and using the worst case scenario of the scenarios during optimization. But again, it looks like very nice. Your margin has gotten smaller and so on in this case. The problem is this is now robust to the scenarios you gave it. So if your scenarios are wrong, if there's like an other scenario in between, this plan might no longer be robust. Studies show that the robustness holds quite well, but it's really hard to quantify if this like holds in between. There are certain pitfalls with robust optimization that can be quite drastic. So for example, I once have seen a study on robust optimization where basically someone evaluated 3 millimeter shift scenarios and the spot spacing was exactly 3 millimeters. So basically shifting your plan by 3 millimeter kind of just moves the spot onto the next spot laterally, and then basically your scenario is kind of a very biased case, your worst case scenario. So that's just like some things. It's very easy to overlook something. Although, like as I said, many like some people investigated this and really said, yeah, in the cases we investigated, also other cases that are not under the scenario seem to be covered reasonably well. But never forget this, that you just have a very limited view on your uncertainty space. As an alternative school, there's like the stochastic and probabilistic optimization, which tries to capture more of the uncertainty space by really sampling from the distribution. So that's another way to quantify uncertainty, not through worst cases, but by sampling from the distribution. So for example, you say my 3.5% or 3% range uncertainty is now a standard deviation to and my samples can come from in between there. The same holds true for stochastic for setup, but for images it's of course like more difficult to think about this, because usually you have a discrete set of images. So there the worst case approach or the scenario based approach makes more sense because you cannot sample that easily in between. But yeah, it's a very natural way of quantifying uncertainties. You again do a repeated dose calculation, and then you get like some distribution over your dose plan metric or optimization objective, and you can use these moments that you get, the mean, the sample mean or the standard deviation, also to, for example, then parameterize a distribution. There are also ways that allow you to do this analytically or like really in closed form, but that's something that we like or I like, and is not that that prominent or used. So, and what you can then do to plan it, for example, you can just use these statistical moments to use them in planning. Limitations that you have there, here it also really depends on the number of samples. So basically, usually to get a good estimate of expected value or like and standard deviation / variance, you need a lot of samples, and you do not enforce classically robustness. So you look at average values. So like there can be one outlier in the one direction, one outlier in the other direction, and it can be very bad. And you really don't look at it. It's not given in the average or the standard deviation. They don't very well show these values. So maybe just, but it's a different way of thinking about the problem. So you don't look in scenarios, you don't look at scenarios, you really look at moments. So for example, if you have a nominal dose here on a prostate case, you basically, the expected dose or the sample mean of your scenarios will look like a degraded version of this dose. So you expect less dose at the border of the target volume here, for example, because the uncertainties act mostly in the gradient regions, and you see this also in the standard deviation. The standard deviation is high in these gradient regions. So it's a different way to think about uncertainties in those, or how basically they create. The nice thing is that for basically all uncertainties where you need to make an assumption, like for example, how far does the patient shift? What is the uncertainty there? Do I maybe have a machine parameter like the divergence of the beam that is somewhat uncertain? You can basically sample from this and make such an analysis. And you can describe also your whole uncertainty set as a multivariate uncertainty set, and then you can do multivariate sampling. Of course, you need more samples, but it goes quite naturally. So I also want to make a small excursion, like thinking about this not as a stochastic sampling, but really probabilistically. I do this excursion because I like it very much, and I spend a lot of time in this, and Hans-Peter also spent a lot of time of this. So you can basically illustrate this also with very simple thinkings like range and setup uncertainty by thinking how it acts on the individual pencil beam if you assume that that you now have a range or a setup uncertainty. And basically, since the lateral profile of a pencil beam looks quite similar to a Gaussian, it's almost a Gaussian, and the depth profile is like the Bragg peak, you can start just looking at uncertainties by doing explicit moment calculations. So you really can analytically compute this and then see in relation, for example, what an increasing lateral standard deviation would do. So you really see that the expected dose degrades with increasing standard deviation, and you get these horns of standard deviation in dose in the gradient region. Okay, and for the Bragg peak, what you basically see that the expected depth dose degrades a lot as soon as you start to get like a little bit uncertain. It's already at, let's say, 2%. Your expected dose is quite low. And if you have like a lot of pencil beams interplaying and they pass different tissues and you might have different uncertainties, you end up with explicit scenarios that kind of degrade or demodulate, you could say, the homogeneous dose region, and it becoming very heterogeneous. So that's like just with mathematical considerations, you can have quite some insight there into what happens to the individual pencil beam. And you can basically also extend this to looking on a whole plan. So here I have as an example a prostate treatment plan. That's the Madrat prostate patient and the Madrat liver patient. And basically you take just a set of samples with this very interesting way of sampling that we found. And so basically here you see that these changes or these uncertainties, when you sample scenarios out of them, that there's quite a big probability space and there different things can happen. So for example, suddenly a hotspot shows up here And it's not that easy to cover all these uncertainties with sampling or worst case. Here you see quite a good example of basically range overshoot coming from a shift. So basically, as soon as here's a little bit of lung, and when you shift basically bragg peaks that into lung, like something that is here might shift into the small lung patch here, and then basically you get and like this dose horn here of a bragg peak that suddenly was supposed to stop here is now due to a shift stopping back here, or like the stopping is kind of degraded over this lung patch. So there's like a lot of things that can happen and that are very difficult to capture in dosimetric analysis. Okay, so just to give you a little bit of idea how you would do or how you would use such sample information to do optimization. So you would, for example, look again at an uncertainty set, but this time it's sampled and it might be a lot more scenarios usually. But also you could do this optimization with 5 scenarios if you want to. And this time you evaluate during optimization always all objective function and then compute the sample mean or the expected value if you can compute it directly, for example, with an analytical method. And looks like this. So now you optimize the mean over the objectives. And that's just how it's called. So these are like different techniques. And here, like again, consider the limitation is you optimize the average. You're not particularly robust against some scenario. You're optimizing the average. And you can argue, and people are arguing also, what is better? Like, do I want to be robust against the worst case, or do I want to be better on average? So what is the important thing for the patient? And I think it might become very interesting, like the interplay of such methods with imaging. So because when I have to assume a worst case before planning, and I have imaging available, which might like give me a whole different idea of the worst case, maybe some other method might be more suited, or it's exactly the other way around. So it's very difficult to say what would make more sense. Here's an example of such a stochastic optimization, again, using this sampling on a paraspinal case. So here's the spinal cord. Here you have a region, basically here you have the target and the lung situation. And you see that basically here the uncertainties induce also quite some heterogeneity in different samples from the dose. And if you do stochastic optimization, this plan is kind of better on average. But you don't know. This is like just some samples. There might be worst cases, and you cannot really say how probable they are intuitively that you do not cover. Okay, I will talk a little bit about 2 other sources of uncertainty now. In particular, one was already covered by Joao Seco before. It's like the interplay effect that happens when you try to deliver during motion. So that's something particular because, like, especially scanning methods, you always have this delivery patterns that you go through. So basically you scan, like for example, like this is your scanning pattern, then the energy switches and you have the next layer and it has the scanning pattern again. And this takes a certain time. And so a lot of things can happen there basically. You can, do you always like start, for example, at the same point in the breathing phase? Or like, is this the same starting point as you planned? Is the duration of the energy level switch for synchrotrons, for example, and so on. And if here's like a dose plot where you see it's not here for this case, it was not that big of a difference, but it's still seeable. So in the first delivery sequence over some breathing phases, there was like kind of a hotspot here, and then this hotspot vanished and became somewhat a cold spot. So you see there is some uncertainty there. And I think here also Joao Seco already told a lot of things about especially what we need to do in the treatment room, maybe with this also like thinking about daily adaptation, but there's also rescanning and some work on how to incorporate this in optimization. So rescanning means you rescan so basically you have another scanning step where you choose different patterns to rescan um, 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 the tumor to make sure you cover it and don't have these cold or hotspots. And I found it really nice that Joao Seco also said, never forget the biology. So because actually this is sometimes in all this discussion of range uncertainty and setup uncertainty and motion uncertainty and delivery uncertainty and what so on, like especially when we go to ions like carbon ions, we have biological models, and these will be covered tomorrow, I think, much more in much more detail. And the problem here is that these models can be hugely uncertain. And if you just look at a simple Bragg peak, I do not want to go into detail on these Gaussian components. We use them for explicitly calculating the uncertainty here in mathematical closed form. But in principle, you now have like this like huge uncertainty band if like your biological parameters have large uncertainty, which they from the papers at least sometimes seem to have. You have like a large, quite large, consistent, systematic uncertainty band around your depth dose. So, and this is like, you can be a huge uncertainty. So if you, for example, let's see if I can play this, because it's something that Hans-Peter just sent me. So if you sample from this, like your Bragg peaks in principle can do whatever they want. So that's like really a very, very, very high uncertainty assumption, but still you see, if you have such a strong biological uncertainty, you basically don't know anything about your Bragg peak anymore. And it's quite interesting to think about how we want to incorporate this, because it's just a systematic uncertainty. If you want to do this in a plan, or look at this in a plan here, where you see this is basically a plan where you um, look at look on the uncertainties. Basically, this is the expected dose, so it looks quite normal. And if you don't look at the biological uncertainties like you do here, you would have this, okay, I have distal edge uncertainty, that's range uncertainty in my liver case. But if you have like this whole systematic biological uncertainty, basically you have a standard deviation everywhere. And what do you do with it? Do you just escalate the dose so that you are sure with your model? So it's really not that simple. And it's really an uncertainty that we should never forget, because often like this whole robust blending, it cares about range uncertainty. For protons, that might be suitable, of course, but as soon as we go to ions, where the biological models are like really, we have multiple models, we have LEM in 4 versions, we have MKM, we have SMKM, we have other models. It's like it's quite can be quite a big difference, and you start to wonder if the uncertainty stays that large. What do we do actually? Okay, so in a summary, ion therapy is particularly sensitive to uncertainties, and we have like multiple sources. There's like, I always say etc., because like you always get a question, but there's also this uncertainty and there's also this uncertainty. Worse, they might be correlated or uncorrelated, you don't know. So at the moment we stick with not with margins. So like in some anatomies, you might stick with margins when they are particularly static. But in principle, you really need this personalized consideration of uncertainties with these techniques like robust optimization, like really quantifying your uncertainties, make an uncertainty analysis. And yes, I think that's what you should take away from that. It's always now has become not a generic margin, but really a personalized uncertainty thing, especially for the more complex cases, and really consider also the other talks. And you see how much research and resources go into like covering these uncertainties. Better fixation techniques, better imaging, range verification techniques, like the robust optimizers. It's like really, you get the feeling that most of the resources and research is going into how do I get rid of these uncertainties, or how do I minimize them. So it's really one of the huge topics, or the huge topic to deal with in ion therapy. So thanks a lot for your attention, and I can answer some questions now.
Thank you very much, Niklas, for all these details. I mean, it's no wonder that specialized personnel is needed with so many things to take into account for these therapies. No? So you see here the questions. I think it's better that we take them now before lunch.
Yes, I think
Yeah,
we can do it.
yeah.
Is it
So
possible to use
calcium with a
protons
little. Yeah.
for stereotactic radiosurgery if we take into account range uncertainties? I have to say I'm not very um, knowledgeable in stereotactic radiosurgery, since you probably go to through less tissue there. It might be even less uncertainty there. But I don't want to make statements because I'm not very into this topic. There's someone else should probably answer.
So, Niklas, I don't think you need protons for stereotactic. The
Mhm.
uncertainties are so small and
Yeah,
photons are so good at it. And keep in mind that the stereotactic the normalization is usually done at the 60%, not usually
yeah,
at the 95%. So you have an error of 1 millimeter. So technically, you would not need protons for stereotactic in
yeah,
the brain. So it's not really needed. You have, yeah.
yeah. So next question is thanks Joao, is the range uncertainty affected by the technique used in the image reconstruction of the CT? That's actually a very interesting question. And I have to say that this is maybe also something that is not really looked at, because these reconstruction techniques, they often focus, or the people that research them, like the natural focus is to get the best image for the radiologist and not the best image for the radio oncologists, in a sense. So it's usually tuned for diagnostic images. And so I think I'm not aware of publications, but I also haven't checked or something like this. But it's a topic that really is, to me, also at the moment not clear what's the impact there. But I guess that you could have better reconstruction techniques that focus on getting a good dose calculation, and not I don't think that you can cover like the things like the conversion with it, because there's also other aspects that happen. But I think you could tune and maybe get like few point something percent out of the error by doing let's say task-based reconstruction, and not a like that focuses on planning and not on and dose calculation, and not on a good image quality, in a sense. But I don't know, it's a very hypothetical question,
So I
I would
think,
say.
Nicholas, I think the big problem of the filtered back projection is if there is missing projections.
Yeah.
It's very sensitive to reconstruction if there's missing projections. So like if you do a 4D CT, for example, there's always these missing projections and you have all these artifacts.
Yeah.
So it's true if you have missing projection, and so iterative reconstruction is ideal because it deals with the problem better. But it's not researched. It's something that's not really
Yeah.
heavily studied. So you're right. It's something.
Yeah. Yeah, because I don't think if you I like Jair Sensor approached me with this and asked me, like, what if we in iterative reconstruction put some metric that tunes our reconstruction for dose calculation? Could we improve this? Might be interesting to think about, but I don't know how big the impact is that it would generate. Okay, please, I'm sorry to ask a general question for patient optimization of dose and please, why the +7% and not -5%? Actually, I don't know at the moment the limit of this, but I have to read the question again. So if I understand it, you basically, this prescription has a like stricter tolerance on the underdosing and a less strict tolerance on the overdosing, which you could argue in a sense would make sense, because underdosing is usually basically negating your treatment. Your tumor is more likely to survive, and overdosing might be more acceptable. But I really don't know. Really can't I don't have it in my mind. So
So I think the 7% is a bit arbitrary. It really depends on the clinicians. The 5% is the 95% coverage that you mentioned. That one is really important. But the hotspot areas is a bit arbitrary. Clinicians can go to 10%. They can go a little higher, and also depends on the organs that are close by. So the hotspot is a bit arbitrary, but the 95% is not. So that one is really important.
What are some examples of biological uncertainty parameters? So the biggest thing here is basically the biological model and knowing what biological properties your tissue has. So basically you first need to derive the biological properties of your tissue. How does it react to radiation? Then you need to encode this in a model and derive parameters for that model, and then the model needs to be accurate. So that's like a lot of steps that can go slightly wrong and might accumulate.
Yeah, and just one more comment, and also typically you do like cell line experiments with clonogenic cell arrays where you then derive the radiosensitivity, but this is only true for this very isolated cell line, and this is basically carried out in vitro, but it does not necessarily mean that the in vivo situation will be the exact same thing. So this translation from a cell line experiment to the human living being and how the basically tissue or our biological system responds to radiation is slightly different, or this translation is basically associated with uncertainties. But we will also come to that tomorrow in more detail. And also to the next question regarding the carbon ion tail.
Yeah, but that's like quite easy to answer, and I think it was mentioned. Carbon ions fragment. Like carbon ions is composed of more than one proton, like protons. So protons, they can just like the proton slows down and stops and at some point, but the carbon ions can also fragment into lighter ions like helium, lithium, protons, and so on. So and these have then a higher, because like the carbon ion also carries neutrons with it. These might then have like a higher energy per that and a higher range. So that's the situation. Is the 280 MeV responsible for the RBE uncertainty? No, that's not the main thing. The RBE uncertainty was basically just on the alpha parameter here, so it basically would translate to the other energies as well. What are the typical margins used in proton therapy and carbon ion therapy? Oh, there is a good publication that summarizes the proton margin recipes. Joao, do you know it? There's this publication that makes this.
It's Paganetti 2012.
Yeah.
But this is specific to protons, not carbon ions.
Yeah.
The carbon ion facilities like Heidelberg have their unique system, and in Heidelberg, I think the margins are very fixed. They are 4 millimeters for certain ranges and 7 millimeters. We don't even have a range prescription margin, so it's unique. But I suggest the Paganetti 2012 published in PMB, if I'm not mistaken.
Yeah. But this is the paper. Does it also summarize the different margin recipes for protons
Exactly.
used? Yes, yeah.
Exactly.
And it's the same one that gives the uncertainty estimates for Monte Carlo. Yes, that one is it. Range uncertainties in proton therapy and the role of Monte Carlo simulation. That's a really nice nice publication. It's sometimes, I have to say, it's misused because I said I don't want to say numbers on the uncertainties, because some people, it's like often they just take, like there's a number in there and then it's a percentage and you just take it for your uncertainty estimates, and now we have like this 3% and 3.5% values floating around, and they just come quite uncritically from this publication, or like even don't recognize how this uncertainty is defined. But it's a very good publication that really summarizes and also let's say deconstructs these uncertainties quite well and shows where they come from. Has some good numbers. So really nice publication. Then is it also possible to revise CTV definition in order to reduce uncertainties for proton therapy cases? So the CTV definition is actually a thing that I would not include too much in the range uncertainties or setup uncertainties. Giving you a better CTV definition tells you more exactly where the tumor cells are. It's very interesting to investigate that, for example, for glioblastoma patients or something like this. There's some nice work from Jan Unkelbach in Zurich on how to model infiltration and so on. So you might be able to have a better idea of where you want to shoot, but it doesn't really helps you in the uncertainties that your patient might lie wrong. So it basically gives you a higher level of localization, which then in particle therapy even might be a bigger problem than because you still have your range uncertainties. But it's an interesting topic.
But I think the important point is that the CTV is not related to physics uncertainties. Yes. It's really a clinical margin that the doctor defines. We cannot touch that. It's a doctor-defined margin. We work on top of the CTV, which is the ITV or the PTV, and that's it. But the CTV is defined by the doctor. You have to keep that in mind.
Yeah, and like what is interesting, so maybe we have a project at the moment where we investigate this infiltrative tissue as a tissue mixture, and then you have two biological tissues there. You have like healthy tissue and cancerous tissue basically in the same voxel or in the same region, and you then can try to use both biological parameters to force the optimizer to fractionate or something. But this has kind of that then you can factor in the biology, and you may in the future you may even be able to reduce the biological uncertainties when you know exactly what is in there. But still, that's like kind of guessing what will happen. Ninth question: what is the accuracy level and dose computation in cone beam CT images? So for photon, so you can think of that cone beam images. There's a lot of research on how to reconstruct them and make them as good as a real CT or close to good. For photons, this is of course less of an issue, but that it is actually already an issue shows you that the cone beam CT induces quite big uncertainties, because photons are not so range sensitive. But if like something shows up as an issue in photon dose calculation, it will most certainly show up as an issue in proton dose calculation. And it depends largely on the techniques, on how you reconstruct or synthesize your cone beam CT. So I cannot give you a number, but it's definitely larger than the CT to the Hounsfield units to RSP conversion error that you get from a normal CT. So it's a very difficult problem to compute those there, but I cannot really give an absolute number now, because it just depends on the technique that you would be using. But it's one of the big hurdles in adapting a plan, that you need the range information.
Okay, I think we are done with the questions. Thanks for answering. And before closing, to remind the participants that